My name's John Huntley. I'll be the chairman for this first session up till the coffee break. We're starting off with a plenary talk by Philippe Brugada from the Novartis Research Centre. It's entitled Multiphase Flow Enigmas in Inhalation Delivery.
Thank you very much. Thank you very much, and thank you very much for returning after lunch. It's a pleasure to be here, not only because I'm one of the two industrialists on the participants list, so I'm pretty much of a rare bird here, and also I'm not even a mathematician, I'm a physical chemist, a colloid scientist. So it's a pleasure to talk to such an audience. I don't know what you're going to make of what I'm going to say. Hope you'll find it interesting. I certainly will be looking forward to your questions and the possibility of discussion. The pharmaceutical world is very big, as you know, and when we go to conferences, as I was doing in December in Edinburgh, we tend to talk to 500 people at once. So to be able to talk to 50 people, it's a real pleasure. So one dreams that one might be able to engage in a form of conversation with you. Anyway, the views I'm going to present today are entirely mine. They're not Novartis. I work for Novartis. I get a salary from Novartis. But today, I've decided it was going to be my opinion. There's a very good reason for it, and I'm not going to tell you why. These are my opinions. So don't go around telling that Philippe Brugada, representing Novartis, has been saying X, Y, and Z. He hasn't. He's representing himself today. Anyway, what I would like to talk to you today is about problems that we have in the pharmaceutical industry in trying to model powder flows in the world of inhalation drug delivery. So what I do as a colloid scientist, I develop drug for the treatment of asthma, of cystic fibrosis, COPD, anything that might happen in your lungs, including problems with cancer. I work with powders, not exactly dense powder flow. There are certainly powder flows because they flow down your lungs, but they're not exactly dense. They start as a form of lump, and they end up as a cloud. So they're anything between a static lump to a very dilute cloud. So not exactly static, and they're not exactly dense either. They start at dense and are very dilute. But anyway, I'm going to talk to you about the problems that we have and the sort of solutions we try to find coming from the world of physical chemistry to resolve the issues that we have. And of course, there's a big gap in the middle, and I hope you can help us to understand and fill in that gap. So what are we going to talk about? We're talking about puffers. This is the product by our competitors, GSK. This is the famous Ventolin. You recognize it? It's blue or gray, as it were, if you get the right hue. Anyway, this is what I'm going to talk about, inhalation delivery. What happens? We fire a cloud into the lungs, it goes via the throat, and somehow ends up in the alveoli. Now, even to get that sort of videos, we need people to help us, and you are these people. That video actually comes from the University of Loughborough. Now, in life, everything goes back to Loughborough. Whatever you do, you try to escape, but you always go back to it. Who is chairing this session? Someone from Loughborough. Who organized this conference? Someone from Loughborough. Who is Sir Wallace? He used to be the vice chairman of Loughborough. Who invented inhalation delivery in the 1950s? Someone from bloody Loughborough. And you know what? Geldart, fine particles modeling. Where is he from? Loughborough. Guess where I worked for 9 years? Well, quite. Anyway, never mind. I'm now in Sussex. And it's rather pleasant. But anyway, let's go back to CFD modeling. This is very interesting. This is for you, maybe you look at it and you think, oh, CFD modeling, just another computer gimmick. For us, it helps us to understand what's happening when we deliver drugs to the patients. Where is the drug going to land exactly? Because we're talking about systems that are extremely small. The little blue dots that were flying happily in the throat of the patient are actually 1 to 3 micrometer. We can't even talk about diameters, they're totally shapeless things. And that's a real problem for us to visualize what's happening. There's no optical system that enables us to visualize what's happening. And of course, we can't fire the laser down the throat of the patient. That's not done. Anyway, even if you could do it, I don't think they would allow it. So we can't see what we deal with. And we have to rely to we'll have to rely on surrogate methods like modeling to really understand what's happening. So what are we aiming for? We're aiming for the alveoli for most of the time, the bottom of the lungs, okay? But in the meantime, we have all sort of systems, all sort of diameters, and the particles need to fly down all the way to the alveoli at the very bottom. And depending on the size, they're going to land somewhere in the trachea, somewhere in the branching systems, or eventually to their target. But in fact, their targets are all over the place. Depending if you have asthma, cystic fibrosis, we may need to target particles in certain regions. And again, we have no real way to understand and visualize where the things are flying. We can do scintigraphic imaging of patients, but it's an ensemble value. It's at equilibrium. It's when the patient has breathed in and is rested. To really understand what's happening dynamically, we need you, and we need the tools of physical chemistry. This is also telling us that the sort of particles we work with need to be very small, and we're talking about 1 to 5 micrometer, not diameter, but sort of most characteristic size. As you can see, the sort of particles we work with are extremely diverse. They start with, here in this corner, budesonide crystals. Budesonide is a major drug that you would use if you have asthma. It's a long-acting system. And so that's a long particle, but that's useless. It's useless in terms of therapy for the patient. It's very good in terms of efficacy because it's the crystalline system. However, people realize we can't fire those particles down in the lungs. We need to modify them. And these are sort of candidates we play with. These are sort of hedgehog type of particles. Very good to reduce interactions between particles, impossible to manipulate. As soon as you touch them, as soon as you try to make them flow, you might disturb the system, and they're very brittle. Therefore, you might disturb that beautiful particle into little fragments, and then you lose the efficacy of your delivery system. Then some people have been trying to copy pollen particles on the top left-hand corner. And there you have porous particles made artificially by people in San Carlos. But now they belong to Novartis. We bought them on the 1st of January. So they now belong to us. And they make porous particles of drugs. It's a very clever system, and we're very pleased to have them on board. Other people have tried to make sort of crumpled particles, like you would crumple a piece of paper. Again, very interesting flying characteristics, but again, extremely brittle stuff, and we don't know how they flow exactly when we try to fill in a capsule to eventually put into an inhaler so someone can breathe it in. And then on the right-hand side, we have the sort of mess we would usually work with, sort of a mix of crystals, a mix of sizes, and a mix of particle characteristics. Typically, that's what we work with. Size distribution fairly broad. We're aiming for 2.83 micrometer to have a form of efficacy in the clinic. But in effect, we're actually working with a mess. It's a very broad size distribution. It gets even worse, because in fact, the particles we use are actually composite. We need to use a carrier particle with a smaller particle. So we use a carrier particle, which is about 60 micrometer, mixed with particles at around 3 micrometer. And then we try to fluidize those particles, and then we try to aerosolize them and make someone breathe them. I tell you, sometimes it's a miracle that asthma drugs work, because we don't understand what's happening. And like everything in industry, if it works, don't touch it, don't break it, carry on selling. But we realize that has got tremendous limitations, because our computers are getting better and we're not. So by trying to do science here, we're trying to get a competitive advantage. That's absolutely true. We're also trying to improve the efficacy of the delivery system and to have a form of improved clinical efficacy. But let's face it, we're also aiming at having a competitive advantage. There's no doubt about it. So, to summarize that brief introduction, what do we have? Very highly cohesive powders, a very broad size distribution that are irregular in shape and in surface composition. Now, surface composition as a physical chemist is something that I'm very concerned about, because that dictates the interactions between the particles as well as the geometry. And I'll go back to that in a moment. And in terms of the formulation that we have, we start from a mixture, and we start with roughly 25 milligram of powder as a lump that we're going to try to create into a cloud over about 250 milliseconds. Your breathing pattern is probably a bit longer, but in fact, the portion of it that's efficacious for the particles to fly in is about 250 milliseconds. That's about the sort of time window we have to fire the particles down your lungs. So we're talking about an extremely complex system, extremely transient, highly cohesive. You really wonder, why do we bother? Wouldn't it be better working with avalanche systems, something you might even control, something a more steady state? But that's the way it is, and it's actually quite exciting. Now that I've done the introduction, I would like to present to you 3 problems that we face regarding 3 different powder dispersive systems. The first one will be what we call pressure meter dose inhalers. They're the traditional puffers made up with a propellant. The second one will be problems around fluidization of particles. So, the other way around. I'm going to talk about aerosolization, so creating the cloud. And then I will be talking about synthetic jetting and piezoelectric crystal excitation to fluidize a system. So 3 enigmas, things that we can't solve, things that we understand or think we understand but in fact can't control. And I would like to present them to you as a form of challenges that you may want to look into. And then to finish, I will be giving you some clues of what we're doing to try to understand what's happening. Because we're not totally ignorant of the problems. We do have some tools, but what we do most of the time is to measure particle-particle interaction, and we're not very good at understanding ensemble, bulk properties, and relate individual properties to a bulk system. And I think that's probably where you could help us to modelize, to create that link between individual particle interactions to the bulk system. So the first enigma, why do PMDI reflux? So what is a PMDI? It's a pressure meter dose inhaler. It's essentially a suspension of particles, particles suspended in a non-aqueous pressured liquid or pressurized liquid. And what we do, we take a dose of it, about 60 microliter, fire it up, and then you end up with a cloud that fires down your lungs. So it's a little animation to show you how it works. A valve is actuated, a liquid with a very thick suspension flows down a valve and then eventually is fired into the lung, into an actuator, and creates a cloud. So we start with a fairly concentrated system, a fairly concentrated suspension, and we're going to create a cloud out of it. And this is what happens. This is typically the suspensions as we observe them. We have a white suspension of a drug in a propellant, in a non-aqueous pressurized liquid. And what we observe is, of course, settling or sedimenting of the system with time. But there is one problem. At the same time it sediments, of course, it coagulates. The interaction is such that although we have a form of repulsion, steric repulsion for most of the time, there is strong van der Waals attraction, and there is obviously gravity that brings the particles together. But something else we have observed is as the particles reach the surface, they bounce off the surface. They defy gravity. And sometimes even there are lumps that go up to the surface, and they break up at the surface and flow down. We don't understand why. There's virtually no electrostatic repulsion in those systems. So why does this system bounce off the surface? Why do these particles reflux? We don't know. We've tried to do measurements there and think, well, okay, maybe we don't understand, but at least we could have some quantitative measurements of the phenomenon to have an idea of the kinetics, an idea of the regularity. The problem with the system is we can't fire laser light, for instance, through the system because often it's too opaque. And when it's not too opaque, there's multiple scattering. So we've tried using ultrasound technology to measure the phenomenon of reflux and trying to quantify it. Again, we got a bit stuck. There we got stuck on the technology, the ultrasonic technology itself, that we can't find detectors and ultrasound generator that's small enough to slice off the can. And anyway, even if we had managed to get the information, what would we do with it? Because we are not the mathematicians. We are not the physicists who are able to model the system. So we then end up with a nice stem collection of all these little phenomena. And then we will need to pass it on to you and say, well, can you help us? What do you see in that signal we've measured? So the first enigma is, why do the particles reflux? Why do they go to the interface when they cream and bounce off and off again? Why is that? No electrostatic interaction in non-aqueous systems. None to speak of. If you have an answer, I'd be delighted to hear about it.
What about convection of a gas?
Well, that's a very good, don't forget it's a closed system at temperature equilibrium. So the vapor will be in equilibrium with the bulk. So the convection of the gas is sort of possible. That will happen when you fire, and eventually there is thermodynamic non-equilibrium. But when you are at equilibrium, you're not touching the can. We even thought, well, maybe vibrations. Well, Loughborough is pretty out of the way of everything anyway, so you're not likely to have a train or a tube passing by. So we were wondering what's going to happen, you know. We don't know. Very good point. Carry on. I'm happy to have more suggestions, I tell you. The second enigma is how do DPIs aerosolize? A DPI is a dry powder inhaler. Now, currently, the market for inhalation is 50% PMDI, 50% DPIs. They're particularly strong in Germany, DPIs, because PMDIs work with ozone depleting gases, so they're not too friendly. But that's not a problem in America. They carry on using them, and that's the major market anyway, so there you are. So the next question is, how can we understand the aerosolization mechanism of DPIs? What do we mean by this? If I can play that video. Hello. Oops, wrong. Where is the cursor? Can someone see the cursor? Voila. So you start from a static system, let's say 25 milligram of non-compacted powder, simply held together somehow in a capsule. And you're trying to create, from the dry state, a cloud. And some people have been trying to understand, well, what's the movement of the particles inside the inhaler? And again, that's sort of CFD modeling from a company called ANSYS. Maybe you use their software when you do some CFD modeling. And they tried different models. First of all, a model where there's no collision with the walls. Then a model where there's no collision between the particles. But none of them are really satisfactory. And mostly because of the complex nature of the particles. Most people assume we're talking about hard, spherical spheres. In our case, we're talking about a very complex system of different sizes. So we don't understand why the system aerosolized. They work. That's all we know. We know what we start with. We are able to characterize it very well. We're able to characterize the cloud that comes out of the inhaler. But what's happening inside, it's very complex. There are only very few people who managed to do very good work on it. And again, it's Loughborough. Henk Versteeg at Loughborough University was able to slice up an inhaler and try to fire up a PDA system, the phase Doppler anemometry system, and a PIV, sort of a velocimetry technology. But again, what it's telling us is individual trajectories of particles. It's not telling us very much about collisions, for instance. And are collisions important or not? When I look at the literature from the chemical engineer scientists, I notice they talk always about collisions. There's none of that literature in the pharmaceutical world. Nobody has looked into it yet. So we don't know to what extent are collisions important. Collisions between particles, or collisions within the walls, or simply the pressure within the airflow. What's happening? The airflow is here about 60 liters a minute. And that's what we assume that a patient would breathe in. In fact, when we've got a granny with COPD, she's unlikely to do that. But never mind, we're going to assume that's roughly the sort of speed we're talking about. So we tried to look at systems and say, okay, well, we can't look into the inhaler. Let's look at a sort of a surrogate system. And this is, for those of you who do particle sizing, the base machine is called the Sympatec. It's a dispersion mechanism. It's to measure dry particles. And so you've got a video camera looking at this little thing on the right-hand side. There's a tube there that's full of powder on the left-hand side of the end of the tube. You've got a lot of powder, let's say 25 milligram. And on the right-hand side, you've got another tube, the metallic bit here. Well, maybe I can do it with a cursor. That's the tube. Yeah, all right, fair enough. I will do like that. And then you've got the tube where the powder is contained. And that metallic tube is going to suck the powder out eventually as it travels inside it. So the left-hand side travels around the metallic tube and is going to suck it out. And what we see, depending on the type of powders we use, we either have a nice erosion of the powder or a sudden explosion. So the top one is, you can see the powder that's on the surface is going to fly slowly, and eventually all the powder is going to travel. the bottom one is nothing happens until a certain point where the powder breaks. So that's obviously pointing out to two types of cohesive powders. One is more like sand, so not so cohesive, and the other one is more like what we tend to work with, like you could say icing sugar is the best analogy I can come up with. And why is that? What are the interactions that are leading to this type of behaviors? And how is this affecting the performance of our inhaler? So intuitively, we would say very cohesive powder, very bad system, not going to aerosolize very well, and not going to deliver the particles very well to the lung. And sort of a sand-like of system would mean, well, easy to aerosolize, good performance. Well, in practice, it's precisely the other way around. Cohesion is somehow necessary in the powder for the inhaler to have very good performance in vivo with the patients. It's a very odd thing.
Sorry, the cohesion is the one below.
Yeah, the cohesion one is the one at the bottom, yes. It is the one that's got the best performance when we do our very own test to check the performance of an inhaler, i.e. would give it to a patient and work out the fine particle fraction that has reached the lung, these sort of things. Why is that? This is a very odd, unexpected result. So what is it telling us about our need when we design the system to have very strong cohesive systems? But of course, the more cohesive the system, the more problematic for us it is to manufacture it. Because when we fill in the inhaler in the factory, then we need to have we want to have a nicely free-flowing powder because it's faster and it's better, it's more regular. But to have a good performance, we need to have a cohesive system. Now, how are we going to resolve that quadrature du cercle? I have no idea for us. Okay, what am I talking about when I say powders? Let me give you a bit more information here. I said that the particle was actually a composite system, and it is a typical picture of what we have. We have, that's actually taken from the literature, not from the work at Novartis. We have a carrier particle, which in this case is like a pyramid. That's its major dimension would be about 60 micrometer. And onto it, I grafted the actual particles of drug that we want to deliver to the patient, which are about 3 micrometer. So a huge difference in scale. And the aim of the game is to remove the particle from the surface of the carrier and deliver the particle into the lung while leaving the carrier at the back of your throat. Tricky. But that's what we manage to do most of the time. But how can we control it and how can we improve that system? In fact, how can we get rid of the carrier? Because if I use 100% pure drug system, I'm not going to have a very good aerosolization phenomenon. I need to have the carrier inside. The carrier is lactose. Now, when you're asthmatic and you've got an intolerance to lactose, the last thing you want is to breathe in lactose, okay? So immediately with our system, we have to remove a certain number of patients from those treatments, and that's a bit of a problem. And also, why would you want to give lactose to people when you want to actually give them a drug? But we can't have simply pure particles because they're too cohesive. Now, let me tell you a bit more now about the aerosolization mechanism in DPI as we understand it. This is what we're trying to do. We've got a static power bed, and we want to transform into a dilated powder bed, and then we want to create a cloud, and from the cloud to separate out the carrier from the drug. And all that in 250 milliseconds, not longer. This is tricky, so at least we can say. And if people have been looking at the system and thinking, what do we understand? What are the interactions between carrier and particles? What are the sort of theories and models we can have that we can then use into computer models to really understand what's happening? The first one is what we describe as passivation of active sites, where when we talk about particles, you have to think, okay, they're not homogeneous in size, they're not homogeneous in shape, and they're not even homogeneous in terms of particle characterization. We'll have islands of amorphous material, islands of crystalline material, crystallinity habit 1, and then you'll have another crystallinity habit number 2, and all these cohabit very happily on one particle. So what happens when we prepare the blend that we call the system? Where do the fine particles go? Why is it sometimes easy to pull out a drug from the carrier when other times it isn't? what is it telling us about the surface characterization and the surface characteristics of the carrier and the drug? Why is it that sometimes it's easy? Why is it that sometimes it isn't? Is it that the drug sort of neutralizes certain sites, and as you increase the concentration of drug versus the amount of carrier, you sort of neutralize very active, interactive sites, and then you're left with inactive sites, and it's easy to remove those particles? Or is it another form of theory? That in fact, we have an even more complex system, like a ternary system, when you have a very coarse carrier, coarse drug, and fine drug. And somehow the fine drug gets into the holes into the carrier, blocks those holes up, and then the drugs that is actually going to be effective in the delivery is somehow seated somewhere else on the surface, but not in the active site, not mechanically interlocked. What's happening? And we're all trying to think hard about physical models that we could use to describe what's happening. None of them are satisfactory. All of them are very much Vermutung, how do you say, assumptions. So they all sort of intellectual equilibration, if you want to describe, to use another word. We don't know what to do with them, essentially. That was enigma number 2. What is aerosolization? How does it take place? What is driving the aerosolization? But before we can reach aerosolization, I need to talk about fluidization. Because as I mentioned, we start from a static powder bed, and we want to create sort of a fluid powder bed, and eventually from the fluid, create a cloud. Now, how are we going to create the fluid powder bed? The first thing is obviously gas. So when we breathe in through a mesh, we pull in some gas. And as long as the pressure difference is big enough, then you will create a fluidized powder bed that you will then be able to aerosolize. Another clever way to do it, and that's the technology that Novartis has access to, is through piezoelectric crystal excitation. And that's the latest buzzword in inhalation drug delivery. Its synonym is also synthetic jetting, or what do you call it again? I've lost a word, never mind. Non-mass transfer jetting, I think they call it. Zero mass transfer jetting, where you put a powder bed onto a piezoelectric crystal. It could be a loudspeaker, my goodness, as long as you get the right frequency, that will do. A form of excitation. And somehow that excitation is going to be transferred to the powder bed, and the powder bed will be able to jet through small holes of that cavity. And that is sort of a pure fluidization. It doesn't use gas. Simply uses a form of energy. But how does it work? Could we possibly use that system, for instance, to understand the interaction between the particles? We have a pure excitation, a pure powder bed, no gas flowing, no exchange of matter except eventually the powder flying out. How can we use that system for us to understand fluidization? How does it work is the enigma behind that slide. It works. We can get powder out and into the lungs of the patients. But how does it work? Why? What you have here is a cavity, which is about maybe at the most 1 centimeter high, and an excitation at the bottom. And when you pierce holes in the sort of dome, you will eventually see jets flying out with powder. And I'm going to show you how it works here. Now, why is that? Why does it work? Why simply, I think it's about 40 kilohertz excitation, a movement of about 20 micrometer. How is that capable to create such powerful jet? How is that capable to simply lift up a 25 milligram powder bed of very cohesive powders, 1 micrometer diameter? Well, not diameters, but you get the gist. How does it work? What is this telling us about the interaction between the powders? That's the last enigma I wanted to present to you. And how could you help us to answer that question? It's not simply a question of resonance, and that's sort of a modelization that people have been trying to come up with. Okay, there's a Helmholtz resonance, it's a resonance cavity, and at certain frequency it's possible to lift up the powder bed, and we're able to do the test of the efficiency of the delivery according to frequency. So we can tune in and we can play with a good old oscilloscope and electronic control, and then we end up with powder coming out and powder not coming out. But why? How does it work? My dream is to be able to use that piezoelectric crystal to measure interactions between particles. That would be ideal, because that's what we're aiming for. We would like to be able to understand the powder bed, its interactions, and its relationship to the cloud. Now, I've presented to you the three enigmas. I've presented to you the background of what we're doing and in what system we're working with. Now I'm going to tell you a bit about what we've been trying to do to understand our systems. So the physical chemistry of chemical physics method that we've used. I'm going to present two of them to you. First of all, atomic force microscopy, so particle-particle interactions, and now we can relate that to the performance of the inhaler. And the second one I'm going to talk about is powder rheology. So moving from individual particles interactions to bulk measurements. What do we make of them? How is that helping us to understand the performance of our inhalers? Ideally, I would like to have a third arrow on that slide and tell you how we managed to relate the powder rheology to AFM. I don't think we're going to manage that in my lifetime, but you never know. Things have been known to happen. Now, brief reminder, what is AFM? Atomic force microscopy. Essentially a cantilever, a particle attached to it, a surface, bring the surface next to the particle attached to the cantilever, measure the interaction, either the deflection of the cantilever if there's an attraction, or the repulsion of the cantilever if there's a repulsion. And then you plot the force you've measured as a function of the distance as you approach the particles and the surface. Fairly easy. That's the sort of curve you end up with. You end up a force, being able to plot a force as a function of distance, and from it you'll be able to work out a form of interaction of repulsion or interaction of attraction. And what do we do here? Well, that's the sort of curve we like to see. On the y-axis, we have a measure of the performance of the inhaler. So we started from the static powder bed, and we've ended up with the aerosol cloud. We know the interactions between the particles in the aerosol bed, the powder bed, and we'll be able to measure how much particle comes out, but we don't know the link between the two at the moment. And we're hoping AFM will give us that link. So on the y-axis, we've got fine particle fraction, a measure of the efficiency of the explosion of the cloud, if you want. The number of small particles that we managed to collect. It's the number of individual particles we managed to collect out of the inhaler. And on the x-axis, we have the measure of the interaction between the particles. And of course, the higher the value of the particles, the more cohesive the particles, the lower the fine particle fraction. Now that's what we expect, but that gets more complicated later on. So essentially what we have is, if the particles stick together very strongly, we're likely to see a form of lowered fine particle fraction. But what you see here could simply be a coincidence. We measure interactions between particles in the dry state, then we measure the cloud, and then we put the two together on the same axis. And then even worse than that, we actually select the force we plot on the x-axis. If you look at the labels, you can just about read them. We have here on the dispersive surface energy contribution. So out of the AFM measurement, we're going to take a portion of it that we call dispersive measurement. Essentially, the surface tension, so to speak, of a solid can be divided into several parts. Some polar parts, some parts due to electrostatics, some parts due to dispersive forces. And we decide to plot one element of it, because that's the element we think we can isolate. And sometimes we venture into plotting the total surface energy contribution. But again, that's actually a selected energy, because the models we use from physics probably don't apply entirely to the solid state. Most of them have been developed for the liquid state. Surface tensions, for instance, of liquids, when you try to extrapolate them to solids, you have to be extremely careful. Particularly when you start measuring dispersive surface energy contribution from contact angles, for instance. Hard work. So thermodynamics is probably failing us a bit here, or maybe we're not using the thermodynamics properly how they were derived. We are hoping it would work for us. And in a way, there's a correlation. But for me, that correlation will remain a coincidence until we can prove through a form of modeling that the two are related. So this is our attempt of measuring particle-particle interaction and trying to find a link with the efficacy of aerosol. It's a very exciting link. It's very interesting, but is it true? I don't know. The second attempt at modeling the systems is through powder rheology. I don't know if you people are familiar with that technology. It's called the Freeman FT4. Essentially a cylinder of powder with a blade going up and down and rotating at the same time, and you can change the angle of the blade, and you measure the torque, and you measure the, what else do you measure in this case? Well, you measure the pressure difference, because you can also put air through at the bottom, so you can aerosolize the system to change the interactions. So from a particle-particle interaction, we're now going to move into a bulk measurement of an ensemble of particles, sort of a column of powder. From those measurements, we're going to try to understand something about the powder bed we have, and even relate it again to the performance of the aerosol. And again, we have very good, interesting correlation, which in my view could well be, again, a coincidence. If you plot the fine particle dose, the amount of powder that's come out of the inhaler, the one that corresponds to the small particles, if you plot that as a function of the fluidization energy, which is actually a measure of the torque and the shear forces, and in the column of powder measured by that instrument I mentioned on the slide before, again, you have a nice linear curve. Now, we love that linear curves. They seem to indicate that something is happening. And when you see the more fluidization energy you're going to measure, the more it's required to put into the powder bed to make it move a little bit, the higher the fine particle dose, so the more efficient your inhaler. Ooh, dear. What is that telling us? Maybe the opposite of what I was telling you earlier about the type of interaction that might be between the particles and the type of interaction that might lead to a highly efficient system. So what do we make of that information? We don't know. We find very interesting information. We can measure until the cows come home, you know. We can do all sorts of measurements. We've got all the techniques we possibly want. But what do we do of those measurements? And how we understand them? It's a real difficulty. Another measurement is the aeration energy that we put in. And we plot that again as we plot the efficacy of our inhaler as a function of that energy. And this is what we obtain. And what we see is, as we put more and more fines in the composition of our system, so we put, so think about the three particle system. We've got the carrier, 60 micrometer. That carrier might have some fines at around 10 micrometer, and then the drug is itself 3 micrometer. So what is mentioned here as fines is actually the 10 micrometer carrier. It's not the very fine particles. And the more you put of those fine carrier particles, between 5 and 10, to be honest, the more aeration energy you need to put in to fluidize the bed, but actually the more efficacious, or efficacious our inhaler is in terms of aerosolization properties. And that again is an interesting twist. Why, when you put more in, just 1 minute, is it? Yeah, all right. Why, when we put more and more fines in the system, we end up with a more efficacious system, when in fact we're creating more interactions? This is a completely bizarre system.
Is percentage to all particles or only to carriers?
At the moment, we're talking about lactose with drug, so lactose coarse, lactose fine plus a drug. Of course, then we can start playing games and modifying the carrier. Instead of using lactose, we may want to use trihalos, or leucine, and instead of using drug A, we may want to use drug B, C, with different surface characterization. So, there you are. I've presented you 3 enigmas that we would like to resolve. I've presented you our attempts at understanding what's happening and the limitations of what we know. And now I'm going to leave you with it. Where do we go with that sort of information? What do we do next? Clearly, fluidization mechanisms of these sort of cohesive systems, and I'm very well aware that all the work you've done in this group has been mostly with particles that are above 10 micrometer. Now, I tell you, there's a huge world out there for particles at around 1 to 3 micrometer. It's actually going to get worse, because more and more we're talking about nanoparticle delivery to the lungs. So we're going to talk about even more cohesive systems, and then no one knows what's happening. It's especially in air. If we were talking about suspension of nanoparticles in water, colloid chemists could come to the rescue and help you to an extent. With our system, it's not the case. We need to model aerosolization systems, and then we need to find models that link formulation characteristics with product performance. Thank you very much.
Very much, Philippe, for a very interesting industrial application. We have some questions.
Philippe, how much your data or Novartis data, in other words, can we use that data? Because you are right. I mean, there is a world which is down there with very small particles where cohesion has importance. And we have done some work actually on cohesive particles where we have something for the bulk, and what we have to infer is just that kind of force that you are measuring with the AFM.
Mm-hmm. So how much of it belongs to Novartis? Very little, actually.
Yeah.
Because
I think it would be extremely interesting to see whether with that kind of measurements that you have and the kind of constitutive relations that we try to develop on a bulk, at the bulk level, things can be modeled.
A lot of it has been published in the pharmaceutical journals.
No.
Yes.
It's not. Okay.
Yeah, it is. Yes, you need to give me a call if you want, and I can.
Well, it's funny because I presented some of that data in a seminar at Loughborough, and I was just checking my transparency here, and they are named Loughborough, so there is some Loughborough there. But anyway, yes.
University of Bath, University of Sydney, the university in America, I can't remember which ones, North Carolina somewhere. Then Nottingham University has published a little bit AFM data. Imperial College had some. If you use my name, you will find some link to publish data.
Yeah, but it would be nice to apply. I mean, we have done some other applications, but it would be nice to see whether it actually can work in this kind of system. That's why I was
It was a very interesting talk. I mean, but not very industrially. So I'm interested. The first question, the main question is the conservation of linear momentum. You showed this piezo, you had this powder, and then you had this sort of enormously fast jet of fine particles. What is it? 99% of the linear momentum is stopped by the. You take all those things which collide, right? And then you have things which go away.
Yes.
Very fine particles go very fast. What is the amount of the linear momentum which is going through, the flux of linear?
I don't know by heart. That has been measured. There are a couple of publications available.
No, what are we talking about? I mean, it's 10%, it's 99%, 99.99%. I mean, about that sort of order.
I can tell you the amount of powder that comes out is in excess of 95% of the powder in the blister will come out. Of the powder.
Not the stoppers, but the carrier.
Well, no, I mean to both carrier and powder. They really explode. No, 95% of it will come out of the blister. There's very little left behind. Even the carrier comes out. The holes are much bigger than the carrier. So most of it is actually very efficient. But it's a very new system. The company who developed it was trying to sell a variant of it called microdose. Has published very little, which either mean they're sitting on information or they never had it in the first place. Anyway, I don't know. And they've published very little information. In the past 3 years, a couple of people have looked into it. Boehringer Ingelheim, our competitors, have published lately in April last year in America at a conference, some information about it. People are trying to do some work, but it's terra incognita for most of it.
No, so it's very interesting. The second question was, why doesn't it plug that? Of course, because 95% of the body come up, which is good.
Sorry. Hello.
I think just time for one last question. I think he was first.
One of the you've shown that a higher strength in the agglomerate basically gives you better dispersion. You can artificially create a little more strength in the agglomerate by increasing the pre-compaction of it slightly. Does that have the same effect?
Very good point. We don't do it because it's patented by AstraZeneca. What they do, and that's my former employer at Loughborough, they create pellets or little balls of drug and carrier, which have about, in excess of 100 micrometer diameter. So it's a composite ball, and that curiously aerosolizes very well. But if we start to copy that, we'll get into hot water at Novartis anyway. In academia, you'll have more freedom to play with that system.
But it has the same effect?
Yes, it does, yes.
Okay.
So, because for years we've been trying to have non-cohesive system. We thought, oh, we can't have cohesion. And then suddenly you realize actually cohesion helps to have fine particle fraction.
It's the elasticity of the particle bonds, isn't it?
Well, or an
Storing
explosive rupture of
energy.
the cake.
And also collisions of large objects, I don't know.
Yes.
It's the effect of if you have gunpowder in a pile and you ignite it, it just fizzes. But if you put it in a barrel and contain it, you get an explosion. That's the same effect, sure.
Oh, that's interesting. I'll look into that. Righto?
Yes.
We'll have to go. Right?
Yeah, sorry to interrupt this very interesting discussion. So, maybe we have to stop there. Thank you very much once again.